Welcome to a lesson with Dr. Powell. Let's take a look at how we can find area in polar coordinates. So in general, what we're looking at is kind of like the rectangle in polar. So a constant R value and theta changing. So a little d theta. So this is kind of like a rectangle, right? Because theta changes a little bit and the function or R value stays constant. But instead of looking like a rectangle, it looks like a sector of a circle. This is the basic shape, and adding up little pieces of this finds you the area. So what is the area of a piece like this? Now for a rectangle, we would say R times d theta. But for this sector, we have to think a little differently. So we take the fraction of a circle that this is, which is d theta over 2 pi, realizing that d theta is the radian measure, and the total radian measure all the way around is 2 pi. So this is the fraction of the circle that we're interested in. Now the circle that we're interested in, we're taking a fraction of the area of, has a radius of r and an area of pi r squared. Notice how the pi's cancel. And so the area of this basic rectangle shape is simply r squared over 2 d theta. So in general, if we have a function r of theta is equal to something, then to find the area traced out by this curve from the encapsulated from the origin out to the curve itself, we're adding up the areas of sectors, we simply compute r of theta squared over 2 d theta. Now keep in mind, when r is negative, that's okay because it's made positive here in this area calculation. So you really don't get any cancellation in that case. So even if we have a curve that has some loop-de-loops and some negative r values in there, going back and forth, actually doing this computation should still yield the desired full area that we are after in all the loops. Since what we are integrating in this area formula, we take to be positive. Thanks for watching.